Hello, my name is Richard Benson. I'm the Dean of the College of Engineering here at Virginia Tech, and I would like to spend a few moments with you to talk about the Joseph F. Ware Jr. Advanced Engineering Lab, or Ware Lab as it's commonly known. The Ware Lab was started in 1998 to address a need for a common location on the Virginia Tech campus for undergraduate engineering students to design, construct, and test competition vehicles for various regional and national competitions. The Ware Lab consists of over 10,000 square feet of space, allowing 19 different teams to work on projects in an environment conducive to learning and innovation. Teams from mechanical, civil, aerospace, and many other engineering majors have shared space, resources, and their own ideas to build a formula car, a steel bridge, and a vehicle for blind drivers, just to name a few. Many Ware Lab teams place in the top 10% at competitions, and participation in these events allows students to develop important communication skills through interaction with colleagues from universities around the world. Visitors to our lab are impressed with the level of sophistication and the detail of the projects being conducted here, and they enjoy talking with our students. Our Hokie engineers are Virginia Tech's best representatives. They demonstrate the hard work and commitment needed to succeed in national competitions. If you are visiting us here at Virginia Tech, please make plans to stop by the Ware Lab. Tours are arranged for groups and individuals by completing a survey located at the lab's website. Enjoy the Ware Lab.
Hi, I'm Micah Boswell from the Autonomous Underwater Vehicle Team here at the Ware Lab. And the Ware Lab really gives us an opportunity to work on a very multidisciplinary team. The Autonomous Underwater Vehicle is a robotic submarine that we build to compete in an international competition every year. The vehicle is designed basically to complete an obstacle course underwater completely autonomously, meaning we have no control over it. This means the project includes a lot of aspects, not just mechanical and ocean engineering, but also electrical and computer engineering, and even computer science. For example, the students that are designing the hull of our vehicle, that might be from aerospace or ocean engineering, work closely with the electrical engineers and computer engineers that are in charge of wiring everything together and all the electronics and everything that has to go inside the hull, things like that. So every student gets a better understanding of what it's like to work together on a team. The Ware Lab also gives us a unique opportunity to have a lab space that is open to the students 24/7, meaning that we can come into the lab and work on things on our schedule, not dependent on our professors or advisors or anything like that. It's all up to the team, how we want to work on things and how we want to get things done. The competition that we participate in involves a lot of different elements as part of the course, including obstacles that test navigation, maneuverability, computer vision, and also acoustic sensors. So on the vehicle we have various sensors to help accomplish these tasks, like a camera here at the front to capture images of the course, and it processes those and makes decisions based on that data to figure out where it needs to go. For this task of the competition, the vehicle has to autonomously locate this buoy underwater and basically drive up to it and touch it to indicate that it's located the object. Building an autonomous vehicle is challenging, but putting it underwater adds an entirely new dimension of difficulty. We have to account for everything from the density of the vehicle to how to keep things waterproof, especially with electronics. And of course, as an undergraduate design team, there's no way that this all could have been possible without the help of our sponsors. We have received grants from Lockheed Martin, the MathWorks, the Student Engineers Council to help us buy all of the parts that went into this vehicle, and also fund our travel to the competition and help us represent the university. A good bonus of the competition is that it exposes all of the team members to dozens of different companies that come to the competition looking at all these different projects that are all potential employers for team members.
Hi, my name's Stephen Porter, and I'm on the Autonomous Underwater Vehicle Team of Virginia Tech, and we work out of the Ware Lab currently. One of the great benefits of being on our team is that we're a very multidisciplinary team, meaning that we have a lot of different majors working on this project. I'm an aerospace engineer, and a lot of the other engineers are aerospace, ocean, mechanical, electrical, computer science, and even computer engineering. What's great about this for me is that I get to learn a lot more about the electrical and computer engineering and computer science aspects of this project. The Autonomous Underwater Vehicle Team of Virginia Tech goes to a competition out in San Diego every year where we attempt to take our vehicle, the submarine here, and navigate an underwater obstacle course. What we have to do for this obstacle course is we have to do various things such as maintaining a constant heading according to a compass, hitting different obstacles such as buoys like this, where we have to hit the buoy. We have to first locate the buoy, be able to see it with our camera that we have located at the front of our vehicle. We have to see it, be able to home in on it, and actually strike it. After that particular task, throughout the competition, we have to do slightly more difficult tasks up until we get to some of the most challenging tasks, such as recognizing silhouettes of objects like this, a battleship or a bomber or anything else like a factory. And we have to be able to distinguish between them, such as between this one and the bomber you can see in the background. And we have to be able to locate them and drop bombs on them, or basically just little balls that we have loaded into the vehicle.
My name is Eric Donovan. I'm a senior mechanical engineer here at Virginia Tech. I'm one of the team captains this year for the Virginia Tech Baja SAE team. The Baja team is a senior mechanical engineering design team that each year we design, build, and race a single-seat off-road vehicle like the one I'm sitting next to. We also compete annually against other universities throughout the United States and throughout the world also. We go to competitions that test the vehicle's acceleration, maneuverability, and durability. Each year we start from scratch. We start with all the skills we've learned in design throughout the fall semester, and we design until we can start building. We start fabricating towards the end of the fall semester, and we have a running car by the beginning of February. And then we go to one competition that allows us to test the vehicle a little bit. We have a test track that the university has given us some land, and we have built a test track to somewhat simulate the conditions that we'll see at competition, which allows us to fine-tune the vehicle. From there, we just keep testing, and if something breaks, we redesign, we evaluate it, we redesign and fix it. And then we have our main competition that we go to, which is in the spring, where we compete against about 100, 120 other teams throughout the U.S. and the world. And this year we competed in Michigan in the middle of February. We drove up there and it was a snow race. We competed against about 40 other teams and we took first place this year. From there we came back and then we went to Greenville, South Carolina for the main SAE, which is Society of Automotive Engineers. We went to the main SAE race in Greenville, South Carolina. The main SAE competition tests the vehicle in many different ways. We have 4 main dynamic events that we compete with, and we also have two or three static events. The static events are cost and design. We must present our design to judges that are industry reps. We also then test the vehicle's acceleration with an acceleration pull. We also do a pull event, which is we're hooked up to some type of vehicle or small ATV and pull at a certain distance. We also have a maneuverability course, which is a very tight course, usually through the woods, going around trees, which tests the vehicle's steering design and how tightly it can maneuver and how quickly. And then we also have a suspension event, which takes the vehicle through a very rocky and bumpy course, going through a pothole section or logs, railroad ties. The big main event is the endurance race. It is a 4-hour-long race over a course that can range from anywhere as short as a mile to several miles. And it's a course that has varying terrain from just a dirt road to a very tight, twisty section of turns and jumps. We are given a 10 horsepower Briggs & Stratton motor that we're not allowed to modify. This is from part of the SAE rules. Because we're not allowed to modify the motor to gain more power, our main focus is weight. Generally, the car takes anywhere from $15,000 to $20,000 to build, plus the added cost of competitions, which can range from $5,000 to $10,000 depending on where we go and how many trips we take. We've been very fortunate over the past several years to have great sponsors such as the Student Engineers Council here at Virginia Tech and also the Ware Lab. We also, every year, we talk to industry reps and companies to get sponsorship from them.
The Blind Driver Challenge was first proposed by the National Federation of the Blind Jernigan Institute in 2005 as an incentive to develop a vehicle that can be safely and independently driven by the blind. In 2006, Virginia Tech was the only university to take on this challenge, and today we're making great strides for developing new novel blind access technologies.
Mounted here on the front of the vehicle is the Hakuya laser rangefinder. The laser rangefinder functions as the eyes of the vehicle by detecting objects in a 180-degree field. The distance to these objects is then measured and plotted in polar coordinates by our software. This allows us to create a map of any hazards around the front of the vehicle.
All the information from the laser rangefinder is input into our National Instruments Compact Rio, and using a software program called LabVIEW and a motion planning algorithm, we're able to interpret and analyze the data from the laser rangefinder to be output to our interfaces called Drive Grip, AirPix, and Speed Control.
One of the BDC interfaces is known as Drive Grip. This system communicates steering angle to the driver during operation of the vehicle. The system consists of a 4-fingered pair of tactile gloves with vibrating motors on each one of the user's hands. These motors will then activate in order to communicate steering angle to the driver. The system integrates the turn with the user's hands by communicating the need to turn right or left during operation of the vehicle by gradually activating the motors in the direction that the vehicle is intended to gradually turn.
This is AirPix, another one of the innovative devices designed by the Blind Driver Challenge team. It was designed in response to a request by Dr. Mark Maurer, president of the National Federation of the Blind. He said that like many blind people in America, he takes in a lot of information through his fingertips and his hands, and so he requested a refreshable or updatable tactile map that would give him information to his hands about what's going on outside of the vehicle in terms of paths and other obstacles. So we designed and created this, AirPix. It's basically a plate with a grid of orifices through which air can flow, similar to an air hockey table. Except unlike an air hockey table, we can individually control the airflow through any one or group of these orifices, creating a pattern, a point, a line, or a shape. So the user simply places his hand over the airflow and is able to see what is going on outside the vehicle. One of the most exciting aspects of this device is our ability to give information, not just instruction. Instead of telling the driver, oh, you need to turn to the right or you need to turn left, we're actually able to give the driver information about what's going on outside the vehicle real time, allowing him to make his own informed driving decisions. So we're really excited about this project on the team, and we're proud of the work we've done so far.
Another interface that we developed conveys speed control instruction to the driver. Our design utilizes strategically placed motors in leg straps and in the right shoe. Vibration on the left leg strap instructs the driver to press the brake pedal, while vibration on the right leg strap instructs the driver to press the accelerator. Vibration in the tongue of the shoe tells the driver to press down on the pedal, while the vibration in the heel of the shoe instructs the driver to lift off.
The next generation Blind Driver Challenge vehicle will be based on a street-legal Ford Escape hybrid. The ultimate goal of the project will be a final demonstration in July of 2011.
Through this new platform, the team hopes to create a vehicle that can break society's stereotypes and create a path of technology to promote the capabilities and independence of the blind. Thank you.
Hello, my name is Adrian Massey. I'm a rising senior in the Edward C. Via College of Civil and Environmental Engineering. I'm originally from Albemarle, Virginia, just outside of Charlottesville. I came to Virginia Tech originally as a hospitality tourism management major. After being accepted in the College of Engineering, I chose the civil path, and with that, I was looking for another challenge, something to do during the semester, and I found the concrete canoe. I, like most people, wondered what exactly it was. I went to a couple of the meetings in the early fall, and I was pretty much hooked after that. What we would really do is every year there's a competition. It changes through the host schools in our region, and every year they set up different dynamics for the canoe, structures, I guess the design for it, and what's actually put into the canoe. What we try to do is we try to make concrete float. We go through things. Concrete is very strong in compression, but not very strong in a tensile strength. So one of the first things we have to do, we have to try to find out what will keep the boat from cracking when we put it in the water and people sit in it. We actually use a geogrid polycarbonate mesh fiber that holds the tension for the canoe for us. And then our next object is we need to make this as light as possible. Concrete itself is fairly heavy. This boat behind me, I think, weighs just around 200 pounds, believe it or not. You know, easy enough to be moved by a couple people. If we had a block of the canoe itself, we could just throw that in the water and that would float. We will actually do most of our work in the structures lab. We have a little bit more room there, where we display everything here with the rest of the team in the Ware lab. We break up to a couple teams. One team is in charge of designing the mold for the canoe. Another one is working on the mix. And then we have peripheral jobs, like, you know, we need to build a carrier for the canoe. Like, it's not exactly easy to move around, and, you know, the less stress we can put on it before we put it in the water, the better. This year, you know, I think our final compressive strength of what we decided for the mix that we're going to use was around 5,200 pounds per square inch, I guess. So it was it's pretty good. And the weight was actually about 58 pounds per cubic foot, which is quite a bit less than the weight of water, which is 62.4 pounds per square foot. Regular concrete's usually about 150 pounds per cubic foot. So, you know, it's a lot lighter. Some of the reasons for, you know, why we want the boat as light as possible is once we've designed it and built it, we actually race it, which is a lot of fun. This year we were up at Catholic University in Washington, D.C. They put on a great program for us. After we do the design and the display, and we get judged for how we actually build the canoe, then we race it. There are usually several relays. One of them is a zigzag, where we actually have to make about 6 or 7 turns, including a U-turn. It's usually the most tiring race, but they put us out there first. And after that, we do a group of 5 sprints, 2 with guys, 2 with the girls, and then one's the co-ed.
Hi, my name is Ben Giobbi. I'm a junior in aerospace engineering, and I'm a member of Virginia Tech's DesignBuild Fly team. Our team consists of mostly freshmen, sophomores, and juniors in aerospace engineering. We give students the opportunity to get their first taste in what it takes to test, design, and build an aircraft created to achieve a specified set of goals. At the 2009-2010 AIAA DesignBuild Fly competition in Wichita, Kansas, our team placed 16th out of 69 teams overall. Our plane, Veni Vidi Vici, was the 4th fastest at competition, and our loading scheme was the 3rd fastest at competition. Next year's AIAA DesignBuild Fly competition will be held in Tucson, Arizona. We'd like to thank Lockheed Martin, Futaba, Microtech, SolidWorks, and the Virginia Tech Ware Lab for their continued support.
Hi, I'm Evan Horetsky, a senior mechanical engineer on the VT Formula SAE design team. I've been working for the past 2 years as a mechanical engineer on this design team, designing and fabricating an F1 style race car. We compete every year at Michigan International Raceway against 160 teams internationally. What makes Formula SAE unique is that, unlike other design teams, we spend an entire year on the development and the design and the engineering for preliminary design behind our vehicle, and then we take our entire senior year and we fabricate it. So what you see here is a vehicle that was built primarily by Virginia Tech engineers. We sometimes send some of our fabrication out just because it's more economically feasible, it's a better design. But most of what we do, all the bodywork you see here, all of the chassis, suspension, A lot of the engine components are done in-house. Some of the highlights of the Formula SAE car is that it has a 0 to 60 time around 3 to 3.2 seconds, which is about as fast as a Ferrari Enzo. We have lower CG this year, around 9.5 inches. Personally, I'm the electrical team leader on the team, which means I'm in charge of all the electronics. Being a Formula SAE, a Formula 1 style car, a lot of people think it's mostly a mechanical achievement. We can't have any drive-by-wire, we can't have any throttle-by-wire, but there's still a monumental need for the electrical system. The engine is run by an engine computer or an ECU. We have a data acquisition system where we need to pull in data for all of the designers and the drivers to have. We develop and design our own dashboard that can give adequate information to the drivers. We also have a lot of safety measures that electronically cut ignition and spark with the car. There are 4 sub-teams on the Formula Design team this year. We have the chassis or the suspension sub-team. We have the engine or engine and powertrain sub-team. We have drivetrain sub-team, and we have the electrical sub-team. All of these engineers and designers are Virginia Tech students, part of the Virginia Tech Student Design Program, our senior capstone. What we do is we go into a class our first semester of our senior year, and most students then pick a design team from there. You can see in the Ware lab there's the hybrid electric vehicle team, there's blind driver, there's Baja. These are all different senior capstone design teams that we're involved in, and we choose our first semester of our senior year. What's unique, as I said, about Formula is you come on your junior year as a 2-year design cycle. We go through an interview process, we have tryouts, we have cuts. This car cost over $100,000 to design and fabricate, and that includes our preliminary testing costs, our failures, our redesigns, our carbon fiber work. And the way we get this sponsorship money is through considerable grants and funding from the mechanical engineering department. We get a lot of great funding from the Society of Engineers, the SEC Council. We also have, as you can see here, a variety of sponsors that help us out with materials, with processing, with endowments that allow this team to perform at the level it needs to for competition. When we go to Michigan, and sometimes we have a state competition in Virginia, there's a great need not only to perform well in what's called dynamic events, which are like the acceleration, drag racing, the autocross, the endurance runs, but also in what we call static events. These static events include a sales presentation where we simulate a marketing team that has to sell 115 of these weekend racers to a client, and we have to talk about Lean Six Sigma, lean management, a lot of the same marketing and sales engineering that we're going to experience in the workforce. We have a cost presentation where we go over our bill of materials. We get checked on the fact that we designed for manufacturing on this vehicle. And then finally, we have a design presentation where we present to a series of judges who are professionals in the industry, racing engineers, race car team members, automotive engineers, Honda, BMW, Ford. All of their best and brightest come to grill us on whether we actually spent engineering analysis and devoted our time to learning the fundamentals of engineering to design this vehicle.
Hi, I'm Rachel Dobroth. I'm actually a communication major here at Virginia Tech. I expect to graduate this May. That sets me apart from the rest of the engineers on the hybrid electric vehicle team. Instead of working on the actual car, my responsibility is to help with the outreach components of this competition. Outreach components include things such as media outreach, such as telling local papers and TV stations about what the team is doing and the certain events we're getting into. And other components involve reaching out to youth, such as in the middle schools in the local and surrounding areas, to tell them a little more about our project and engineering here at Virginia Tech in general. In addition to youth and media outreach, we're responsible for an influencer campaign. This means we are to reach out to politicians on a local, state, and federal level. Currently, we're building a relationship with Mayor Ron Wardham of Blacksburg, and with that, we tell them more about our car and really try to get the town council involved as much as possible. We're also looking to reach out to state and federal delegates in the House of Representatives, that kind of thing, to really tell them about our project and how important this green innovation and new technology is to us here at Virginia Tech, as well as throughout the EcoCar competition, since that really is the true goal. The engineers with the hybrid electric vehicle team are extremely lucky to work with wonderful companies. Argonne National Laboratories, who manages the EcoCar competition, helped set up partnerships with companies such as National Instruments, who provided us the hardware in the car. GM, as you can see, donated the car behind us. A123 Systems designed a specific battery pack just for the engineers exactly to their specifications. And then MathWorks also provides the software that makes the whole thing possible and makes our hybrid car work to the best of its abilities. The car that the HEVT engineers have designed is really unique. It is a hybrid, which is similar to some cars on the market, but there are certain aspects that set our car apart from the rest of the competition. For instance, this is a split parallel architecture, and what that means is we have the battery power in the back, which powers the rear axles, and then we have a 2.4-liter flex fuel engine in the front, and that actually runs off E85 ethanol, which means it's 85% ethanol and 15% petroleum. By doing this, we get away from gasoline and towards a more renewable, clean-burning source. As I mentioned the hybrid, we actually have a plug-in hybrid, and this means that our battery is big enough and more powerful enough to power the car on its own for about 40 to 50 miles. This is what we refer to as charge depleting mode. Once you've driven long enough to deplete that battery to a certain percent, the flex fuel engine will kick on in a matter of seconds, and you're going just like a normal car, and that'll start to charge the battery, charge sustaining mode. And at that case, you get the same abilities as if around-town hybrids that you see on the market now. So it's as fuel efficient as possible, while still maintaining a lot of the great qualities that you see in an electric car as well. There are also two unique aspects I want to highlight about our hybrid in particular. One of them is that we have regenerative braking. What this means is that anytime you press the brakes in the vehicle, no matter if you're at a complete stop, it turns the rear motor into actually a sort of generator, which will in turn power that back battery to give you more electric power. Also, we have engine idle stop, which means that anytime the car comes to a complete stop, say at a stoplight, the fuel engine is able to cut off, and therefore saving you from the idling fuel use.
Hey, I'm Jonathan Murrow. I'm from Newport News, Virginia, and I'm a member of the Human-Powered Aircraft team. This is a senior design project at Virginia Tech, and it's been continued on for the last 4 years, and we're picking off where the previous teams have left off. So basically, the design started 4 years ago when a group of seniors in aerospace engineering decided they had heard about the Kramer Prize, which is a prize given out in England for anyone that can meet certain aircraft criteria, and it's all human-powered, meaning that a human must propel the vehicle by themselves. There's no motor aid given, and it was started in the 70s, and the first prize was won around 1977 by Paul McCready and the Gossamer Albatross. And basically we're trying to win another Kramer Prize, which is the Kramer Prize in Sport, where the aircraft has to fly around an equilateral triangle that has certain dimensions, and it has to do it in a specified period of time, which is 3 minutes each way, counterclockwise and clockwise. And so the last 4 years we've been trying to design an aircraft that can meet these criteria. So it's really cool to work on this project because we get to get down and dirty and come to the Ware lab and actually build something. The first 3 years, this is the 4th year of the project, the first 3 years focused on the conceptual design and the preliminary design, which basically is all the paperwork, the calculations, the analysis, and the computers. And so this year it's all culminated into finally constructing the vehicle and actually trying to get it to fly.
My name is Mike Kaskis. I'm the Human-Powered Submarine Team President here at Virginia Tech. I'm from Frederick, Maryland. I graduated from Urbana High School in 2007. I am a junior in Ocean and Aerospace Engineering here.
I'm David Borden. I went to high school at Leonardtown, Maryland, Leonardtown High School in Southern Maryland. I'm currently a junior here, also dual major with Ocean Engineering and Aerospace Engineering.
Here at Virginia Tech, the Human Powered Sub is run through Ware Lab, and anyone can be involved. I got involved when I was 11 years old with the race people who run the International Human Powered Sub races. My dad was a judge. I started out running paperwork between the two different judges, and I did that for 2 years, and then I got my scuba certification, and I started doing underwater photography. And I would spend about 40 hours underwater a week shooting video. And I came back as president of the team when we competed in Carter Rock, Maryland last summer.
This here is a Phantom 6, our previous sub. We are currently building a new sub, but this is the one that is based off of. This is a wet sub, meaning that it is fully flooded with water. The pilot breathes off of scuba gear, and he lays flat on his stomach, so his head is up there, and the back is here. We use on this a variable pitch prop, which means we can change the angle of the blades depending on what speed we're running and how the pilot is performing. We also use in this sub a linear drive system, which means it's propelled by pedals that go straight in and straight out, and this allows us to slim down the hull so that it's less drag. Most teams and what we had in previous subs use more like a bicycle pedal, which requires a rotation of the legs and a fatter sub.
So our team here is divided up into several different crews. We have our propulsion crew, which builds our propeller and our gearbox. Then we had a control crew, which they design the rudders and the control joysticks on the interior. We have a diver and safety crew. They are in charge of maintaining all the scuba gear, dive operations when we compete underwater, our safety items like our emergency buoy here, which we have a switch on the inside, so if there's trouble, we release it and the buoy floats to the surface. We have a computer crew. They design and build a computer which interfaces on the inside. It can record data, for example, like our RPMs and our speed. There is our hull crew. They're in charge of designing the actual hull and the fiberglass section of the boat. There's two competitions that alternate every other year. There's one in San Diego, California, and then there's one in Carter Rock, Maryland. And at competition, you're judged on your fastest submarine, best design innovation, best use of composite materials, your teamwork with your team. This past summer we competed in DC, or Carter Rock, Maryland, and we won 3rd place in design innovation. And there we compete in what's called a tow tank. This tow tank is 22 feet deep, 50 feet wide, and 3,500 feet long. Now we only use 100 meters of it, and that's how far the race course is. It's a 100-meter drag strip. And you race against the clock, but then at the end of the week, what the staff will do is they'll have 2 subs race side by side for top speed.
We have people on the team from all majors, including history majors, philosophy majors, and then mechanical, electric, and ocean and aero engineers. We take all majors, and most of the people on the team find that there is some part of this design which corresponds to classes that they're currently taking.
We're currently in the process of building a new sub. It's called Phantom 6. It is about the same size of Phantom 5 right here, except it's twice as wide. And what that is going to let us do is we're going to have one pilot lay down face first, head up here, and then have another one laying right next to him. As far as we know, no other team has ever done this before. One of the reasons could be with that is because you have 2 people side by side, it can cause the sub to tilt more, which is a problem. Now, to help prevent that, what we're going to do is we're going to have 2 propellers in the back, and they're going to be counter-rotating, meaning they turn in opposite directions. So what we'll do is we'll have our 2 gearboxes where the 2 people are pedaling from, and now go into a gear system which will make each pilot's RPMs merge together, and go out and split the two different propellers. And this will help us from having a centrifugal force that will roll the sub. Now, in the back there, you can actually see half of the hull that's molded on fiberglass. That's actually the bottom half, and that's actually 5 layers of fiberglass. The top is 3 layers of fiberglass, and it has a foam core, and that helps us with buoyancy, and also helps us from rolling. Because there'll be a floating force up top, and we'll put a few weights in the bottom. And those two forces help prevent you from rolling back and forth. A few of our major sponsors here, Collision Plus locally. What we do with them is we take our hull, it's made of fiberglass, we sand it, we bring it to them, they'll help us finish out the bumps, and then they'll paint it for us. We have Mox Epoxies, which donates our fiberglass, a little bit of carbon fiber we use, and all the epoxy. That helps us cover our costs for competition, our costs for when we go testing. Because when we test, we drive down to Wekiwashi Springs in Florida over our spring break. We spend a week down there in the springs where we have about 100-foot visibility, crystal clear water, and we just test the sub on a fake course we set up.
This is the robot of the Virginia Tech IEEE hardware team. The team is an undergraduate research project that has been around for decades. What we do is every year we get a challenge by our parent organization, which is the IEEE, and they give you a set of rules and a goal. And this year's goal was to build a solar-powered robot that would complete as many laps on an indoor track as possible. And they put a couple things in our way, like ramp obstacles that would be tough to climb. They put height and width obstacles that would limit the size and dimensions of our solar panels. As you can see here, they're pretty small. And we had about 50 teams competing this year at the competition, which is called Southeast Con. Every year it's held at a different southeastern school, and this year it was in North Carolina, Charlotte, North Carolina. In previous years, it's been in Huntsville, Alabama. It's even been in Jamaica. This year, even though we didn't win, we were still in the top 12 out of 50, which is it's pretty decent for us. We're happy with that. But it was definitely one of the more challenging projects that I've ever worked on. I don't think I've ever invested this much time in a project or worked with so many people. There were 14 people on the team this semester, and the previous semester there were 18. One of the other difficulties we have is that it actually gets really hot under these work lamps that you see. These were specified by the IEEE for the competition, and even though we're not trying to complete the project to their specifications anymore, we had them, so we're going to keep using them. But these are 250 watt halogen work lamps, and what we have found is that even though we get about a quarter of the power that we would have outdoor under ideal lighting conditions, this thing actually gets really hot. This thing has a giant capacitor array on it, and capacitors are like little tiny batteries, but they don't keep their charge when you disconnect them from the system for very long. So part of the rules for the competition were that they were going to discharge these capacitors so that they didn't have any power in them, and then they were going to turn on the lights. And you had 3 minutes to drive around this track, and that included the time it took for the capacitors to charge up to whatever voltage you needed them to be at. All the teams are initially in this giant practice room. It's kind of like a green room for competition, if you will, and they have some practice tracks set up. And we saw robots that were blasting around the track 10 times in 3 minutes, and we thought we were going to get obliterated by these teams. And they get into the competition room, and not only is the competition room pitch black, but the lights are hung a little bit higher off the ground, the robots a little bit further away from them. And they sat there and they didn't do anything. The team designed and built over half a dozen circuit boards by themselves for this thing. And in addition to, getting little Radio Shack boards and soldering on, very simple integrated circuits, we designed some pretty complicated stuff, and we actually sent it out, and it was fabricated professionally.
My name is Brendan Wayman. I'm one of 7 students that's working on the Solar Decathlon project at Virginia Tech. The house is called the Lumen House, and it has competed in the 2009 Solar Decathlon in Washington, D.C., and it will be competing in the 2010 Solar Decathlon Europe, which is in Madrid, Spain. And in between, it has been on a couple of road trips to places like New York and New Jersey to showcase on some television shows. I'm from Chesapeake, Virginia, and I came here with an interest in things like physics and sustainable design and engineering in general. I chose mechanical engineering because it was a broad field that you can work in, and this project interests me because it was a different kind of mechanical engineering project other than cars and planes and boats. One of the key things that I enjoyed about it was that sustainable design, and it allowed me to introduce my engineering background in a way that could be better for the environment and also can help residents in the future save some money. Our team is comprised of 7 students, and we also have a faculty advisor. We have a couple of volunteers that have joined on midstream. We started out working with a completely designed system, so we essentially inherited a complete system and had to learn the ropes pretty early on at the beginning of the semester because our competition was only a month away. This proved to be a daunting task because it's actually a pretty complex system. I've grown very knowledgeable about the heat pumps and how they can be implemented in homes and have high performance and high efficiency as opposed to current HVAC units in houses today. I've learned about things such as geothermal and how this can be used for more efficiency when heating houses and cooling houses, and essentially using the earth to work for you and the earth's constant temperature at 10 feet. On this project we work with a wider range of people. We work with architects, computer science, electrical engineers, structural engineers, building construction, and also mechanical engineers. This house was designed by the architects with 2 key points, responsive architecture and net zero energy. Responsive architecture means that the house is intended to adapt and respond to the outside conditions and also the inside conditions, things like the temperature outside, whether or not it's raining, if it's day or night, and also if the user is home. And also active, we have a water-to-water heat pump and water-to-air heat pump system tied into a geothermal loop to allow us to efficiently heat and cool a home and maintain comfort levels at a very low cost compared to a normal residence.
My name is Jenny Kanatsi. I am a graduate student here at Virginia Tech, and today I'm going to be telling you a little bit about the Steel Bridge team and what we do here. There's about 20 people on the team, and in the fall semester we design our bridge, and in the spring semester we fabricate it, and then towards the early summer we go ahead and we compete in competitions both in Virginia, Maryland, and DC, and then a national competition later on. And I guess we have 2 sponsors who helped make this possible this year. They were both Nucor and Hirschfeld. In RISA, what we do is we model our bridge in 3D. First we model in 2D and then in 3D. And I guess we use ideas from past bridges where we have the general idea, and every year there's a new requirements for what we need to do. There's a different profile for where we can build, and there are limitations on both where we can build and I guess the length of the bridge and the depth of the truss. In the spring semester, we decide how we're going to fabricate it, which is usually a pretty interesting process, I think, just because a lot of the things that we discuss in design, they won't work, or we'll have difficulties with them, or we'll need to modify things. And so we make modifications and start talking about how it's going to be fabricated. It's all welded. I guess we have a couple different pieces of material. We have
A36 steel and chromoly. The chromoly is a higher strength steel, and it's a little bit lighter, and that really helps us out in the competition. And we weld everything. We use both MIG and TIG. Last year's bridge, there was a slightly different profile, and so I guess you could build further out, and you could also have a deeper truss. And having the deeper truss really helped with the bending of it and getting the stiffness that we need. I guess this year's truss, we had to decrease the size by about a half a foot, which meant that we had to have a much heavier, use more material in order to get our moments of inertia up to where we need them to be. I guess we had just recently had a regional competition which involved all the schools in Virginia, in DC, and in West Virginia. And we actually became first place in that in every single category. That would be construction time, structural efficiency, and lightness. And we'll be advancing to nationals, which is coming up here in a couple weeks, and we've got some modifications that we'll be working on. I guess I would like to tell you a little bit about the pieces that we have. Each of the pieces, it has to break down into a piece that's at maximum 6 inches by 6 inches in the dimension across it by 3 feet in length. And so I guess this is about the right size of what we would do. And each of the pieces, they slide together. We fabricate it here, and then all the pieces get assembled at the competition, and we get timed on it. And we get judged on aesthetics, which is a small portion of the score, and then on the lightness, on the stiffness, and on how fast you can build the bridge. And those are the 4 main categories. And I guess last year we did extremely well. We came in 4th at the national competition out of about all the schools in the nation, but there were 50 schools that advanced to the national competition. The bridge can carry, I guess with the loading sequences, how it's loaded at the competition is we apply 2 grates. They're actually the grates right back there if you can see them, and they go on top. Each of those weigh about 100 pounds, and then on top of that gets put 2,500 pounds, which is equivalent of a small Volkswagen vehicle. And it gets loaded in 2 different places. One is automatically at the middle of the truss, which is the place, if you load it in the middle, it's going to want to deform more. And the second place is determined on the day of the competition. They roll a die, and I guess the second half of the load can go anywhere from the end of the bridge to the middle of the bridge on either side. And so that way you can't design it for necessarily one loading condition. You have to be flexible with your design and be able to be efficient in multiple loading scenarios.
Well, my name is Chris Moen. I'm an assistant professor in the Charles E. Via Jr. Department of Civil and Environmental Engineering. My background as an engineer started with 8 years in consulting as a bridge engineer. Then after my 8 years, I went back to get my PhD at Johns Hopkins University in Baltimore, Maryland, where I focused on the design and behavior of thin-walled structures, and specifically thin-walled steel structures, cold-form steel, structural components that are used in low and mid-rise construction. As far as student competitions, I was first introduced to the concrete canoe and steel bridge when I was an engineering student at the University of Virginia in the 1990s. I actually ended up being a team captain for the concrete canoe team for a few years and really caught the bug for these kinds of extracurricular activities where I got to explore my skills as a designer. Another benefit of this competition is that students gain the experience of working in teams, and that's a challenge. There's always different personalities that need to mesh, but that's a very important important skill for students to have when they head out to the real world. And finally, and actually probably most importantly, is that the students, as they work through these projects and grind through the details, they gain confidence in their abilities.
Hello, my name is Dan Uke, and I'm with the educational marketing team at the MathWorks. I'm actually a Virginia Tech alumnus. I graduated in '95 and '98 with my bachelor's and master's, respectively, in aerospace engineering. I went to go work for industry for a few years, and because I liked the MathWorks tools so much, I went and joined the MathWorks to help other customers learn to use them well. I've always been in customer-facing roles at the MathWorks, and I've very much enjoyed my time there. I'm here to talk to you today about how MathWorks is privileged to support the Ware Lab. Let me start by talking about MathWorks' role in academia. MathWorks is committed to education, and that is exemplified by its relationships with thousands of universities across the world. It's those programs that teach students the skills and the knowledge necessary to be able to solve today's complicated industry problems. MathWorks also supports numerous global student competitions like Formula SAE, Nerd Girl Solar Car Project, and the MIT Vehicle Design Summit. It is through these competitions that students get access to commercial strength tools and are able to apply and learn MATLAB and Simulink to solve their projects. MathWorks tools are integrated across full curriculums in universities around the world. It is there that disciplinary knowledge and tool knowledge are combined to better prepare engineers for the workforce. MathWorks is seeing more and more design processes relevant to industry being applied in academic curriculum. Furthermore, a big part of academia is around global collaboration, schools working with each other. Nothing is more evident than just taking a glance to the posts on MathWorks' Facebook page. There's over 125,000 fans, and the collaboration is evident. The Ware Lab is a unique facility here at Virginia Tech. It houses over 20 student undergraduate competitions. What do all these competitions have in common? They're all tasked with designing a complicated engineering system from end to end. It is this end-to-end process that will let me talk a little bit about MathWorks tool use with respect to industry usage. On a personal note, a bit of my previous work experience, I worked at Lockheed Martin Skunk Works, and the relation with Joseph Ware here at the Ware Lab also makes it a little bit special for me to be able to contribute in this fashion. I've been told by many students that the skills they've learned with MathWorks tools on summer internships, that they've enjoyed those very, very much. They come back to school excited to share it with their peers, share it with their faculty, apply those skills in their schoolwork and in their student competitions. It's been a pleasure working with the students and having them see the value of model-based design. What I have seen students accomplish in a few short weeks with model-based design, MATLAB and Simulink, and their personal drive has been nothing short of impressive. What I'd like to do is now show you a few specific examples of the work I know about here at the Ware Lab. At the same time, I'm going to show a few demos of the products that are similar in nature to the type of work that's being done. I'm going to start off with the Virginia Tech Autonomous Underwater Vehicle. This happens to be the first team that I had a chance to work with personally. They actually didn't have a functioning vehicle, and we went over some of the capabilities of MathWorks tools and model-based design, and in a few short weeks they were prototyping image and video processing algorithms, control algorithms. They were testing those control algorithms in simulation. They were using real-time workshop to generate code for those algorithms and actually implementing it on their vehicle. I'm truly amazed in the few short weeks, and again, their personal drive and how they ran with it. It's a testament to the leaps and bounds they've made on that project. Another good example is Formula SAE. I've been working with that team for about 1 year now. Very early on, they established a multi-year trajectory in terms of what they wanted to do with MathWorks tools. They adopted model-based design. They began to create component models for various subsystems of their vehicle, suspension system, the drivetrain system. They began to evaluate those systems. They were taking in test data, and they were able to validate their models and also fine-tune them. They were able to do design trade-offs by bringing in these component models and seeing how effects from one component have on others. Finally, they're going to close the loop around this. They have certain goals and requirements that they must meet with their vehicle, and they're going to do requirements-based testing. They'll be able to test against the models, against the model of the complete system, and use those tests also on the real vehicle. And they're able to close the loop and iterate on that. What Formula SAE is doing is laying the foundation. They're laying the foundation to be innovative, being able to communicate their lessons learned to others, and be able to maximize reuse. These are key capabilities that commercial customers see the value in completely in being able to minimize time to market and maximize productivity and profitability. The last example I'll talk about is an XPC Target system that was set up in the main computer lab here. Any student can walk up to this system to learn about model-based design, execute a few simulations, and more critically, concentrate on a rapid prototyping stage of model-based design. This is a stage where the students need to prototype their controller while it's talking to real hardware in real time. In closing, it's been a pleasure to work with the students, the teams, the faculty advisors, and the administration here at the Ware Lab. MathWorks looks very much forward to continued collaboration over the years to come. Thank you very much.
During the last few minutes, you've had the opportunity to learn more about the exciting projects here at the Joseph F. Ware Jr. Advanced Engineering Lab. Virginia Tech's College of Engineering has over 5,000 students and is currently the third largest engineering degree granting university in the United States. Ware Lab was started in 1998 from money donated by Joseph F. Ware Jr., who was a 1939 mechanical and aerospace engineering tech graduate. Mr. Ware went on to work for the Lockheed Martin Skunk Works in Palmdale, California, with an engineering legend, Kelly Johnson. Mr. Ware worked on projects such as the P-38 fighter and the U-2 and SR-71 spy planes. Mr. Ware wanted a facility completely dedicated to undergraduate engineering student projects. Currently, Ware Lab houses over 21 such projects in an operational space of just over 10,000 square feet. Out of the total population of engineering students here at Tech, Ware Lab has an enrollment of just under 450 students, making this one of the busiest facilities on campus. Our engineering students gain excellent instruction in theory and in computational methods during their classroom experiences, and Ware Lab allows students to apply these skills in real time. For example, a student in mechanical engineering can attend a machine design course and apply today's lesson to the design of a formula car or a Baja all-terrain vehicle. Students taking upper-level courses like electrical circuits, structural analysis, and control theory gain a deeper understanding of these advanced topics by putting concepts to work in the design, testing, and construction of competition vehicles and structures. A large component of the work done here at the Ware Lab involves public outreach. Over 1,200 people a year tour our facility, from high schools, scout troops, community colleges, and other universities, along with groups of industry and business. All who visit are impressed with the scope and complexity of our projects. Visitors are even more impressed with the enthusiasm and professionalism of the students who work here. In addition to attending world-class competitions, Ware Lab teams participate in other forms of outreach by presenting their projects at the annual SEED picnic. SEED is Virginia Tech's Center for Enhancement of Engineering Diversity. Teams also present at Kids Tech University forums and at technology fairs in other cities. Without exception, spectators at these events are amazed to learn about the challenging projects students are involved with here at the lab. I'd like to mention and thank our corporate sponsors, who include GM and Baker Hughes, who recently donated a Sierra truck and enclosed trailer, allowing our teams to transport materials and equipment to competitions around the country. Nucor, A123, MathWorks, Autodesk, and Lockheed Martin donate monetary and in-kind contributions. Virginia Tech's SEC, or Student Engineers Council, has consistently supported us over the years, as has OG Racing, Ingersoll Rand, and Black & Decker. Also, private contributions from Marvin and Sue Johnson, John and Elizabeth Downhauer, and Joseph Ware himself over the years allowed Ware Lab to prosper and grow from 4 teams in 1998 to over 20 teams now. If you or your organization would like to consider donating to the Ware Lab, please contact our Campaign for Virginia Tech office at the website shown below. We hope you've enjoyed our presentation and plan to visit us if you're ever in the Blacksburg area. To arrange for a lab tour, go to the website shown below and follow the Ware Lab Tour survey link at the lower left-hand corner of the page. The tour takes about 40 to 50 minutes, and if you plan to visit, please let us know about a week ahead of time so we can arrange a tour guide. We hope to see you soon at Ware Lab, the front door to Virginia Tech's College of Engineering.